In this tutorial, we will learn how to estimate a moderated multiple linear regression model in R. And specifically, we'll do so in the service of estimating differential prediction in a selection context, which is sometimes referred to as predictive bias of our selection tools or assessments that we're using. So to begin, make sure that you have RStudio open as we have here, then go to File, New File, R Script to open up your R Script editor here. And in this window, if we save it, it becomes our R Script file. So I'm going to use the hashtag to make a quick note here that this is moderated multiple linear regression in R, which is a specific type of multiple linear regression. And by multiple linear regression, I mean that there is one outcome variable and two or more predictor variables in our model. And so when we start thinking about multiple linear regression, we have to start thinking about the concept of statistical control as well. And then we put moderated in front of it. Well, this means that it's a specific type of multiple linear regression in which we're looking at an interaction term. So again, we're doing this in the context of differential prediction, or sometimes called predictive bias, depending on who you're talking to, and in a selection context, okay? So we're going to be working with data today that we'll assume comes from a concurrent validation design, which means that current job incumbents were assessed on the different selection tool or on the particular selection tool we're interested in, and about the same time their performance was evaluated, let's say using a behavioral assessment, a performance evaluation, for instance, of their job performance. And so job performance will represent the criterion. And so in other words, we're interested using this concurrent validation design in estimating the criterion-related validity of the selection tool in relation to the criterion that is job performance in this case, as well as to assess whether or not that selection tool we're looking at has differential prediction based on different protected classes, okay? And so we'll walk through that in a little bit more detail in a second. Before we get there, let's set our working directory. And this working directory is where the data file that you're going to be working with is saved currently. And so I know that that data file for me, which is in this case, it's called diffpred.csv, and I'll write that down in a second. Well, I know that that file is located in my H drive R workshop folder. And so if I click run there, I've set my working directory. Alternatively, you could go to sessions, set working directory, and choose directory to do that, and do this by using drop-down menus here. And so the next step is let's read in that data file that I just mentioned is located in the working directory folder. So the name of the data file is going to be, I'll make a note here, it is diffpred.csv. Okay, so a capital D, a capital P, it stands for differential prediction. And it's a comma separated values file, which is easy to read in R. Now I'm going to use the reader package and specifically the reader function from that package to read in the data, because there's certain advantages that come with that. It tends to more accurately read in the data file that you'd probably hope to read each variable in as, which can sometimes reduce steps on the back end in terms of not having to transform a variable from, let's say, factor to character or something like that. It's usually pretty good at reading in dates correctly as well, assuming they're in the right format. Okay, so I've recently installed this package, so I'm not going to do that again. So instead, I'm going to do library, name of that function, and then put the name of the reader package here. It's all lowercase as the sole argument. Click run to access that package, so that then I can come here on this line and read in the data using the read_CSV function. Now I'm going to name our data frame object that we're going to read in diffpred, just for differential prediction. And again, I'm using that read_CSV function from the reader package. And the name of the data file that we're working with here is diffpred.csv. So make sure that's in quotation marks as the sole parenthetical argument here in the read_CSV function. And we're reading it in and naming it diffpred here so we can then work with that data frame object. So let's click run there. Let's click on the name of that diffpred data frame object in our global environment. And here you should see that you have a data frame object, and we have these 6 different variables. Well, really the first one is a unique identifier, employee ID. And so we'll ignore that for this one. But then we have our criterion variable we're interested in here. So this is our outcome variable, which is performance evaluation, perf_eval. And so this will be our outcome. Our selection tool or assessment of interest is interview. Let's assume this is a structured interview and scores can range from a possible 1 to 10 here. And then we have 3 different demographic variables or protected class variables that we can use to assess whether or not there's differential prediction of interview in relation to performance evaluation scores based on protected class status. Now, what we're doing here is we're going to be actually estimating an additive model and then a multiplicative model in which we have a product term between these two variables, between this interview variable and one of these protected class variables, and I'll explain what that means in more details, but that's where that concept of moderation comes in. Sometimes this is called interaction, and the variables that we're going to treat as moderators, even though they're actually going to be predictor variables, but we can say even more specifically they're moderators, are the protected class variables of age, gender, and race here. We'll call our true predictor variable here the interview, and our outcome, of course, is performance evaluation. Okay? So the first thing that we need to do is, we don't need to do this, but let's do this in this case, is to grand mean center the predictor variables, including that moderator variable I just mentioned, for those that are continuous in nature. So those variables that seem to be mostly or somewhat on an interval or ratio measurement scale, we're going to grand mean center those. Now, truth be told, the interaction term or the product term that we'll create, it will still have the same level of statistical significance in the moderated multiple linear regression model that we estimate, regardless if we center. However, if for some reason you want to interpret the predictor variables or the main effects in the context of the interaction, well, then you'd want to grand mean center these variables in order to reduce collinearity between them and the product term or the interaction term that they form. So we're going to grand mean center continuous predictor, and I'll put or moderator variables, okay? And so in that case, if you look here, we really only have 2 variables that we need to center. The interview variable, which is continuous, and the age variable, which is continuous. The gender and race variables seem to be nominal or categorical in terms of their measurement scale. And so if you're interested in learning more about how to grand mean center, check out the corresponding tutorial that's called Centering and Standardizing Variables in R. So quickly I'll run through which variables we're going to center and how we're doing that. So first we need to put the name of the data frame, $, and whatever we want to call the centered variable. So let's start with that interview variable, and I like to put the C prefix, specifically the C underscore prefix here, and the original name of the variable. So this will be the centered, grand mean centered interview variable that we're creating here. Use the left-handed arrow to assign values to it. And we're just going to do some basic arithmetic and specifically subtraction here. And so what I'll do is the name of the data frame object, $interview, minus the grand mean for the sample, which is just the sample mean here. So I'll use the mean function from base R, followed by, let's just copy this in, the exact name of the data frame, $, and the variable for which we wish to calculate the grand mean or the sample mean. And then na.rm equals true, which says remove any na values when computing the mean, and na in R means missing, okay? So I recommend that you include this last argument as well. So we're just taking interview score minus the grand mean of interview scores for the sample, or the sample mean in other words, and this is creating a new variable that's going to be centered, in which we center around the grand mean, which means that 0 will now be the average value for our sample. So should any case have a 0, it means that they have exactly the average level of interview score for the sample. Okay, so let's click run. Okay, so now we have this variable is created, and let's just copy it. We're going to do a quick adaptation to the script here, paste it below, and now we're going to do the same thing, but let's do it for the age variable. And so the age variable is AGE, all lowercase. So I'm just replacing anywhere it said interview with age here. Okay, let's click run. And now let's take a look at our data frame here. So now you'll see we have 2 grand mean centered variables here. Again, 0 on each would represent the sample mean. And so the standard deviation stays the same as the original variables, but now we've done a linear shift in terms of where the mean is. And it's if you want to learn more about why you might grand mean center outside of the moderated multiple linear regression context and just in general regression or simple or multiple or linear regression context, again, check out that Centering and Standardizing Variables in R tutorial, either the written or the video version. Okay, so the next thing that we're going to do is we're going to do a 3-step differential prediction process. And this is actually was, I guess, arguably first brought about by Cleary in 1968. And so sometimes this is called the Cleary method or the Cleary approach to assessing differential prediction, or sometimes called predictive bias. I believe in Cleary's article, it was referred to as test bias, which some people would say that's not the most accurate term to describe this. But what we're talking about is differential prediction here, okay? And I'll show you some visuals here in a second to bring this to life. But this is also recommended by SIOP, so the Society of Industrial Organizational Psychology, their principles for selection. They also recommend using this approach. And there's different variations on this approach, but we're going to do the following 3-step approach here. So first step is going to be estimate the criterion related validity of the selection tool in relation to the outcome variable. So this is pretty standard what you would normally do with the selection tool. And this is just using simple linear regression here, okay? Okay, so the next thing that we're going to do is the next step is assuming that there is some criterion related validity. Well, then let's see if this selection tool or assessment differentially predicts performance based on protected class group, or for different groups, it might have a different relationship with performance. And so specifically, we're going to be interested in testing intercept differences with this second step. So I'm going to type here intercept differences, and this is going to be an additive model, and specifically an additive multiple linear regression model. And this is going to be the selection tool. Well, for space, I won't put it here, but it's the selection tool plus our moderator variable, which in this case is the protected class variable of interest, is added to the model, okay? All right, and the third step is when we're going to look for slope differences, okay? And so this is going to be a multiple linear regression model here. And this is actually a multiplicative model, okay? And so what that means is that we're actually going to be creating a product term here, okay? And so this is where actually moderated multiple linear regression in the most conventional sense comes in at the third step here. Okay, so this is the approach we're using here. It's based on the Cleary method. SIOP advocates for it. This is an approach I would mention. Again, there's been some deviations and different suggestions regarding this approach. One big caution here is that make sure you have enough statistical power, which in typical terms means that you have a large enough sample here. So don't do this with very small samples because you're unlikely to find an interaction or find intercept or slope differences when you have really small samples, and so that can be problematic. So as I mentioned, let's see some visuals here. So if you're looking for intercept differences, which would be that second step, what that looks like is here. Okay, so let's assume that if we just used a common regression line, okay, so a single regression line for the whole sample and ignored gender in this instance, so here's selection tool scores in relation to job performance scores, this dotted black line would represent what we would get. But look what happens if we account for gender as a protected class. And here we can see women in red, men in blue, and we would see that actually this would be indicative here of there's two different slopes here. There's intercept differences. So if you come to the y-intercept here, wherever that's located, usually it's on the axis here, but if it's wherever 0 is, and so 0 could be here as well, depending on if we grand mean centered. And so here you can see that there's intercept differences. And so what that says is that there is some predictive bias in this tool, and that it'd be inappropriate to use a common regression line here, because you could see how that would overpredict for certain people and underpredict for other people based on their protected class status, okay? Here's an example of what would be kind of a classical example of slope differences, which is what we're going to test in the third step. And so here, let's say that this is 0 here on the predictor variable, the selection tools variable here. So this would be the y-intercept. Here we don't see an intercept difference here, but we do see slope differences, okay? Now, in theory, this is all just arbitrary. If you move the intercept around, let's say by grand mean centering, and so maybe the intercept's here, we'd probably find intercept differences as well. But what we're really focused on here is slope differences, meaning that this selection tool predicts performance differentially for men versus women. So in other words here, we have some evidence that there's differences in kind of validity, okay? So for women, it looks like it's not very predictive. So knowing someone's selection tool score doesn't really predict job performance, whereas for men, it looks like there's a positive association there. And this black line would be the common regression line. Okay, so it'd be inappropriate to use a common regression line here. Okay, so this would be suggestive of the fact that, hey, we probably shouldn't use this selection tool because it's differentially predicting performance scores based on whether someone identifies as a man or a woman. Now, this is an example of where you can clearly see it's both slope and intercept differences. Okay, and so you can see intercept differences here, assuming that this is the 0 value on the selection tool variable here, and we can see the slope differences as well. Okay, again, common regression line wouldn't make sense there, wouldn't be appropriate. Okay, so what we're going to start with first is let's do gender. Okay, so we're going to start, I'll actually put it gender because it's all lowercase in the data frame. So we're going to assess whether or not we're going to follow this 3-step process for differential prediction. We're going to determine whether or not we have evidence of differential prediction, either intercept or slope differences based on gender for this interview. Let's say it's a structured interview variable. Okay, and so we're going to use the regression function from the lessR package. So if you haven't already, make sure that you've installed the lessR package. I have recently, so I'm not going to do this again, but this one does tend to get updated fairly regularly. So if you haven't updated the lessR package recently, do so. At the very least, you need to use the library function followed with lessR in the parentheses to access that function. And so you can use the regression function, all spelled out like this, or you can use the reg.brief function. I would recommend using the full regression function normally with a capital R from lessR. However, in this tutorial, to save some time, we're going to assume that all of the statistical assumptions that need to be met for a regression model in order to interpret it, we're going to assume that those have already been met. So I do want to put a word of caution here that this is just like any other form of regression, and it's a specific form of multiple linear regression. So you need to test the statistical assumptions by running diagnostics and so forth to make sure it's even appropriate to interpret your findings. Okay, so those are assumptions like homogeneity of variances and so forth that we typically test. If you want to learn more about how to do that, check out the multiple linear regression in R tutorial, where I go in depth on how to actually assess and test whether or not those statistical assumptions have been met. Okay, so that's a big word of caution here. I'm going to use the reg.brief function here just because I'll assume all the statistical assumptions have already been met, and just to save some space and time, we'll just use this to get an abbreviated version of the regression output from the lessR package. Okay, so first we need to specify as our first argument the regression model. And so it's going to be perf eval. So if we look here, it's perf eval. And then is going to be our outcome variable. Interview is going to be our predictor variable. But remember, we're going to be using the centered interview variable here. Okay, and so let me put a note here that this is step 1. Okay, in the process we're going to be following. So first our outcome variable tilde, followed by C underscore interview, which is the name of that grand mean centered interview variable we created, data equals, and then the name of the data frame from which both of these variables belong to, or to which they belong to, which is diff.pred. Okay. All right. So this is assessing that criterion related validity. Okay. We'll ignore all of this and just quickly move through the output here. Again, this is actually a simple linear regression model. So check that out. If you want to learn more, the simple linear regression in R tutorial. Okay, you can see we have 377 people that we used in the analysis. Here's the intercept value here. We're not usually that interested in this unless we're interested in using this regression formula to predict future cases. And here what we're interested in is whether or not the interview variable predicts performance evaluation scores. So in other words, whether there's criterion related validity, and we see the regression coefficient is 0.307. So this is the slope here. And the p-value is less than 0.05. Here's the 95% confidence interval here to the right. And so here we would conclude that there is evidence of criterion related validity. And if we scroll down here, we'll see that we get the R squared and the adjusted R squared values of 0.129 and 0.127. Okay. And the associated p-value for the model. So if we're comparing this model to a null model, does adding this predictor variable here of the interview scores significantly improve the model fit. And because this p-value here is less than 5, we conclude yes. And so what this means is, well, almost 13%, or rather, interview scores explain about 13% of the variance or variability in performance evaluation scores. So that's actually pretty good here. This would be about a medium-sized effect if we're thinking about traditional effect size or rules of thumb. Okay, so all right, step 1. We found that, okay, interview scores do predict job performance. So that's the first step. So then it warrants going on to the second step. Now, the second step is when we're testing for intercept differences, okay? And I'll just note up here, this is criterion related validity, okay? So when we're testing for intercept differences, this is where the additive model comes in. And so let's just copy that script from above so we can adapt it. Well, here we're gonna use the plus sign and we're gonna create a multiple linear regression model by adding another predictor variable to the model. In this case, it's specifically a moderator variable, and we're going to add that gender variable, okay? So this is gender all lowercase here. And it's in this case, it's a dichotomous or binary variable, okay? So there's the options here are man and woman, okay? And so you might be saying, well, that's not a numeric variable. That's a nominal variable. Well, what's gonna happen behind the scenes is that R, or this function, is going to translate man into 0 and woman into 1, and it does so alphabetically by the value labels here. So that's what's happening behind the scenes. So it is translating this numeric, and I'll show you how to interpret this in a second. So now we have our additive model. Let's click run. Okay. We get our regression output here. We still see we have the same number of people in the analysis, 377. And so here you get your regression model, and now we have two different regression coefficients. We see, well, we have the intercept value, and then we have the regression coefficient for the centered interview variable, and then we have one for the gender variable. This is really what we're interested in here. This is where we can determine whether or not there are intercept differences. So you'll notice that now your gender variable has one of the levels of the gender variable listed after it. And so this is woman, okay? And so what this is saying is this gives you a way to interpret this regression coefficient here. So what this is saying is the outcome variable of interest, which is performance evaluation scores. So it's essentially taking women's scores on that minus men's, okay? And that gives you a negative value. So in this case, this negative value, because it's associated with this value, with this level here of our nominal predictor variable, it means that women have lower intercept values than men do in this particular sample. And so we're going to visualize that in just a second. But we shouldn't interpret this unless we look at the associated p-value, which is less than 0.05. And so therefore we would conclude that this regression coefficient is statistically significantly different from 0. And we can see this reinforced by the 95% confidence intervals here, which are both negative and do not include 0 here, okay? And so if you want to get an idea of how the variance has improved, the variance explained has improved, you can see that now the R-squared value went from about 13.13 to 0.18 for both the regular and the adjusted, or the unadjusted and the adjusted. And again, our p-value is going to be greater than 0 for the model fit, which means that this model does fit the data better than a model without predictor variables in it, okay? But we do see that, at least descriptively, that variance explained went up by about 5% or so. All right, so that means that we have evidence here of intercept differences because this regression coefficient here was statistically significant for our moderator variable, okay? And so the next thing that we're going to do is we need to install, and I'll actually add a space here, and then add some more spaces here. Let's install what's called the JTools package. And I do want to make a note here that depending on when you're doing this, the JTools package is still going to be in existence, but they're moving some of the functions to a new package just called interaction, okay? And so if you try to install the JTools package and you're getting an error message saying that it doesn't exist, or you try to use the following function that I'm going to show you and you get an error and it says it doesn't exist, then just replace JTools with interaction. It probably means that everything's migrated there now. At the time at which I'm doing this, it hasn't officially happened yet, okay? All right, so I have recently installed the JTools package, so I'm not going to do that again, but I will need to use the library function to access it. So library JTools is the sole argument there. Click run. Okay. And what we need to do actually is the JTools package, and specifically the probe_interaction function we're going to use, is not going to be amenable to this type of, to the lessR regression function. So we actually need to specify a regression model and estimate it using the standard base R LM function, which is linear model function. And it's really easy to do this. But one thing that we need to do is we just need to come up with a name for the model that we're estimating. And so I'll just do capital INT underscore model, which just means intercept model. Okay, just this it actually means intercept differences model. I'm just shortening it there. And then we just use the LM function for linear model, and we can just copy and paste right there. The exact same arguments as we had in the reg.brief there. And if you click run, we've now specified this model there. We're going to use this model here we've just specified as input into the probe interaction function from the probe interaction function from the JTools package. Okay, so it's called probe interaction, and as the first argument, let's just enter int underscore model for that regression model. And I'm going to do this on separate lines here for each argument, and then the next argument is pred equals for predictor variable equals, and then you just want to put the name of your predictor variable, which for us we're going to frame the interview variable as our predictor variable of interest. Okay, this is what's going to go on the x-axis, and specifically we're doing the grand mean centered because that's what we use to create this model here. Okay, the next argument is mod x equals, and this is we're going to specify which variable is our moderator, and here we're just going to put gender, okay, because that's what we're treating, the predictor variable we're treating as our moderator here, which is the protected class variable. Okay, now you don't need to put this, but I think this is helpful just to remind ourselves what we're doing here. So let me just do Johnson Neiman equals false, and this is just so we can have reduced output. If we're not interested, there's this, the Johnson-Neiman test is helpful in another regard in terms of probing interactions. It's a little bit more than what we have time to explain in this tutorial, but this would be getting into regions of significance. Okay. All right. The next argument is x.label, and this is where we can give a new name for our x-axis here, and I'm just going to say this is interview score. Okay. And then our last, this is optional too, I'm going to do y.label, and I'll specify a more descriptive name for the outcome variable. I'll just call this job performance. You could call it performance evaluation scores, whatever you want to do. Okay, let's see how this comes out, given that I've really zoomed in the view here, so it might be a little bit more distorted when it'll look like for you. Okay, so here is the interaction we're going to probe. So we're probing the intercept differences model. Click run. Okay, so this gives us a little bit of a visual way of interpreting this model. Okay, so we knew that there was intercept differences. As I said, the intercept for women is less than that for men. Okay, and we can see this reflected here. Okay, so we see interview scores in relation to job performance, and we can see the dotted or the dashed line is women. The orange solid line here is men. And we can see that there is a difference. Okay, and this is, you would only run this or probe this interaction, and at least my suggestion is if you find that in that regression model we ran that the gender variable added that the gender variable and its associated regression coefficient was statistically significant. Okay, look at the simple slopes analysis here. You can see that the regression line, the slope for women here is 0.16, and it's the same for men here. Okay, so now let's move on to step 3. And I will point out that typically you would move on to step 3 even if you didn't find intercept differences, because there could be slope differences that you could detect. But depending on how you scaled your predictor variable, you might not be detecting intercept differences. So let's look for slope differences here. Okay, and this is where we're actually going to be estimating that moderated multiple linear regression model. Okay, so what do we need to do? Well, what we need to do here is we need to let's actually just copy this whole chunk here. We're just going to repurpose most of it. okay, that we used for step 3. So I'm just I'm copying everything we used from step 3. I'm gonna delete the JTools part there. But all we're gonna do to our regression model using the reg.brief function from lessR is just change that plus sign to an asterisk, which just means that now we're creating an interaction term between these two variables. Okay, so what's happening here is that we're actually gonna have 3 different variables, predictor variables, in our outcome variable, in our output, or in our regression model rather. We'll have grand mean centered interview scores, gender, and then the product term or the interaction term between the two. And by product term, what's happening behind the scenes, or the interaction term, you can call it either one. It's just for each person, you would be taking their interview score, or in this case, it's their grand mean centered interview score, and multiplying it by their gender level or value. And remember, behind the scenes in alphabetical order, R is saying that woman is going to be 1, man is going to be 0. Okay, just because M comes before W in the alphabet. Okay, so behind the scenes, what's happening is it would be 0.2448 times 1. So it would be 0.2448 would be the product term there. For this person, it would be 2.0448 times 0. So 0 would be their product term value. So that's what's being created for you. You don't need to create your own interaction term or product term variable in this case. Many of the R regression functions do this in an automated way. Okay, so let's start by running our moderated multiple linear regression model, because this is what this is, because now we have an interaction term or a product term. Okay, oops, I didn't mean to highlight just that. Run the whole model there. Okay, let me stretch out the output here. And you can see we still have 377 people in our sample. And you see now we have our intercept value. And as I mentioned, now we have 3 predictor variables in our model. Okay, the first 2 look familiar. Okay, we've built on that. So we've been building our model here. So in step 1, we just looked at grand mean centered interview. In step 2, we looked at gender. So we created that additive model, multiple linear regression model. And here we've created our moderated multiple linear regression model, because here we have the interaction term or the product term between the grand mean centered interview variable and the gender variable. And this colon here, that's what represents the interaction term, that this is the interaction between them. Now, this gets a little annoying, but because this is so long here, notice that everything's off a column or more in terms of the values. So you need to kind of do a mental shift here. This actually corresponds to the estimate here. So this would be the interaction term regression coefficient. But what we're really interested in here is coming to the p-value, which is this value. So again, it's off, but you'll have to kind of do some mental spatial reasoning here to find this. And so we see that our p-value is less than 0.05 that's associated with this regression coefficient that is tied to our interaction term, which means that we have a statistically significant interaction, which means, in other words, that we could say that gender moderates the association between interview score and job performance here. Okay? And if we come down to model fit here, we see our R squared has now gone up even more, which typically happens when you add another predictor, or at least you hope that happens to the model. And so this is saying that even after we account for these main effects of these 2 variables, grand mean centered interview, gender variable, when we add the interaction term, it explains incremental variance on top of that, because this value is statistically significant here. And we see that in terms of now the variance explained is somewhere between 19% and 20%, depending if you look at the adjusted or unadjusted R squared value. And we see the p-value, again, as you would expect, given what we saw in the previous steps. The p-value for model fit says that when we have these 3 predictor variables in the model, it fits better than a null model with no predictors in it. Okay? All right. So of course, again, you'd want to make sure you're doing all the statistical assumption testing, as I mentioned before, but we're assuming that that all went well. Now, because we found a statistically significant interaction term, we're going to probe the interaction using the exact same function we did before. In fact, we don't even need to change anything here other than the input function that we're using here. Remember, we're using that linear model or LM function from base-R to specify the model. So I'm just changing the plus sign to an asterisk as we did above here. And then I'm just going to change int to slope, or to, let's do slope there. So this is the slope model now. And then just use this as the first argument there. So this is our input now. So now we're saying we're inputting this moderated multiple linear regression model here so we can actually look at whether or not there are slope differences here. Okay. So let's go ahead and run this first line here. Okay, so we've specified that slope model, and now we're ready to use that probe interaction function from the JTools function. And we can keep everything else actually the same here from the previous step, step 2. So I'm going to spread this out here and click run. All right, so this is actually a really prominent looking interaction, specifically a slope difference model here. And we already knew that by looking at the significance level of that interaction term, but now we get this plot here that we're using to probe the interaction will help us visually understand what's actually happening here. Okay? And so what you can see, at least visually, is that for women, interview scores seem to have a positive association with job performance. So actually it seems to show that they have good criteria-related validity. But for men, you actually see what looks like maybe even a possibly negative or maybe just a zero, what we should treat as a zero association between interview scores and job performance for the men. Now, what's great about this particular function is if we come and look at our simple slopes analysis, which will be much more informative in this case, we can actually determine whether or not each level of our moderator variable, if the relationship between our predictor and our outcome variable here is statistically significant. So in other words, is which of these slopes is statistically significant? It could be both in some instances. And so here we'll see that for women, the slope is positive, as we can visually see here, it's 0.26, and the p-value is less than 0.05, so we'd actually say this is a statistically significant relationship. So this seems to show criterion-related validity. The interview tool seems to show criterion-related validity with respect to job performance for women. But when we look at the simple slope for men here, we see that this estimate and the associated p-value, the p-value is 0.77. That's far greater than 0.05. So this slope is not statistically significant. We should just treat this as being no relationship here. So in other words, if we drill down to men specifically, the interview scores does not predict job performance. Okay, so this is an instance in which we would have issues if we used a common regression line here and by mistake and we didn't account for the fact that there are differences by the protected class variable of gender. We would actually overpredict and underpredict men and women are in certain circumstances. Okay, so this is why we probe these interactions, and this is why we do this 3-step process here to assess differential prediction. So what we would say now is, wow, with respect to gender, there's something wrong with this interview variable, this interview selection tool here. It could be, who knows, it could be contamination or it could be bias in our outcome variable of job performance, which was performance evaluations. So supervisors are presumably rating those. Or it could be who is ever scoring these interviews. There might be something weird that's happening here. And for whatever reason, maybe based in part on both of those things or some other factors, we're seeing that interview scores differentially predicts performance, whether the candidate's a man or a woman. Okay, so that's problematic there. And so in this case, we would need to go back to the drawing board, probably redo the interview, figure out what's going on, and or just use an entirely different selection tool to help make our decisions on who to select. Okay. All right, so the next thing that I'm going to do is quickly go through some examples using first a continuous moderator variable, which is age. Okay, so here I'm going to do age is our protected class variable of interest. And then the third one's going to be doing race. And the reason we're going to do race is there's actually more than 2 categories for race. And so that introduces another step that we need to do. Okay, so I'm going to copy the steps from above because we can just quickly go through and adapt them here for age. Okay, I'll show you how easy this is. Okay, so we already have done this first step here. We don't need to repeat it for age, but I just do it here just to show you what's happening, assuming you didn't do gender before this. But we do know that interview in relation to job performance, that there is criterion-related validity there. Okay, so we did find a statistically significant association between interview scores and performance evaluation scores. Now, the next step, we're going to look for intercept differences as we did before. And I'm actually going to delete the JTools information there, assuming you've already installed and loaded that package from above. And we just need to replace age here, or gender with age here, and replace gender with age there. and replace gender with age there, and replace gender with age here, and replace gender with age here, and gender with age here. Okay, so I just went through. You could do if you went to edit and let's see, I believe there, I think if you do a control, if you do a control F, you can do your typical find and replace. You could do that as well, okay, if you want to do that more quickly. So let's now skip down to the intercept step here, see if there's intercept differences with respect to age. Okay, so let's run this model here. Okay, and so here we have, as I mentioned, instead of a dichotomous or categorical nominal moderator variable, we have a continuous variable that is age. Okay, at least how we've measured it here. And now I will point out that there is kind of a debate around age, at least when you're using it for these purposes, depending on, let's say at the federal level, for instance, and depending on which state you're in, you might be protected. Well, at the federal level, you're protected if you're 40 and over. And so you might dichotomize age based on those who are 40 and over and those who are under 40. And then it varies by state too, with certain states having more protections for people that are younger as well. Okay, so without getting into that, for this purpose, we're just going to focus on what happens if you do have a truly continuous moderator variable. And one of the things that's nice about using the continuous variable and not artificially dichotomizing it is that you end up retaining more of the natural variation, and you're more likely to detect differences in intercepts and slopes that actually might exist there in many situations. Okay, so let's look at our output here. So again, we've had 377 cases or people here in our data file or in our analysis that we use. Here's our estimated regression model. What we're interested here in this intercept differences model is this line here, which in this table has our age moderator variable, which is our protected class variable. Here's the regression estimate. Here's the p-value. The p-value is less than 0.05, which means that there is a positive association, a statistically significant positive association between age and performance evaluation scores, which is our criterion. If we come down here to the model fit area, wow, the R squared and the adjusted R squared, 0.256, 0.252. So depending on which one you focus to interpret, or you decide to focus on when you're doing an interpretation, about 25 to 20, or rather, if we include age in the model, in addition to the centered interview variable, that we now have an R squared value that has almost doubled. So if you remember when we just looked at interview by itself in the model, it's about 12% or 13%. And here you see it's about 26 or 25% of the variance explained in performance evaluation scores can be explained by jointly or collectively the interview scores and the applicant or the person's age, okay? And we see that p-value for the model fit is statistically significant as well. All right, so because we found a statistically significant effect for a moderator variable here, now we should probe that interaction, or at least you can if you want to see a visual determination here. But you can, this positive value here indicates that we do see that as people get older, their intercept values tend to be higher, okay? And so let's see what that looks like here by probing the interaction. As before, we need to first specify interaction model using the LM function from base R. So this is just our regression equation here that we did above. So let's specify that. And now let's probe the interaction. So this is everything that we had before with gender. We just swapped out age there. Everything else is the same. Okay, and so now what you'll see happens by default, and this is a pretty conventional way of doing this, is that now we have age at 3 levels. The mean, 1 standard deviation above the mean, and 1 standard deviation below, okay? And also, actually, as I'm looking at this, will be a great learning opportunity, I realized that I forgot to put in the centered variable here for age, okay? And so it won't actually affect the way that this plot looks, but this will, and actually it won't really affect much that we see here. But what you can see here first by interpreting this is that we have the blue line is 1 standard deviation above, the really faint dotted line is 1 standard deviation below. And so here you can see that intercept differences where people that are older tend to have a higher intercept value, okay? All right, so as I mentioned, made a quick mistake there, brief mistake. I forgot to use the centered, because if they were gonna use it, might as well use it. The grand mean centered age variable there that has that C prefix. I'm gonna just copy that into all of these instances here that we see age. And I'll show you how, at least in this context, it doesn't make that much of a difference because we're not really interested in interpreting the main effects of the variables themselves. But it could potentially play a role if we were to have collinearity and so forth between when we get down to this third model here, if we were interested in interpreting the main effects, okay? But we're not really interested in that in the context of this three-step differential prediction model process. We're just using this as an opportunity to practice grand mean centering our predictor variables that are continuous. So let's click run there. This is just redoing that regression model we just ran. Okay, you come up here, you'll actually see that I believe that's slightly different. Or no, it's the same there. So we've actually got the regression estimate here for the centered age variable, same conclusion as before, p-value is less than 0.05. So there is evidence of intercept differences. Respecify the interaction or the intercept differences model here, rerun the probe interaction function there and click run. Okay, as I said, it's basically the same interpretation as before, okay? Because we had already centered interview, so that's the scaling was correct there. And job performance, we're not looking at slope differences, and so here you see essentially the same display. You could export this as well if you wanted. All right, the next thing that we're going to do is let's move on and look and see if there are slope differences. And so here we're just now changing what was a plus sign to an asterisk. Okay, so we're looking at the interaction, the multiplicative interaction between centered interview and centered age here. Okay, so let's click run to run that model and take a look at the interaction term. So we see there's still 377 people here. And what we're interested here is this last line in our estimated model table here. This regression coefficient, which is associated with the interaction term between centered age and centered interview scores. Here's the p-value. Again, these get off a little bit here, but we can see the p-value is less than 0.05, so we would treat this regression coefficient for the interaction term as being statistically significant. So in this case, we would say there is evidence of slope differences, but it's often hard to interpret it in the context of this model by itself by just looking at regression coefficients, and so that's why we like to plot things. Okay, and so the next thing I'm going to do is just run this model here, which is our slope model. Same thing as above, but we're just creating a new slope model. Here's the LM function, the linear model function from base R. This argument structure within is exactly the same here. So let's click run. Okay, and now we have our slope model here entered as the first argument into our probe underscore interaction function from the JTools package. Keep everything else the same if you'd like. Click run. All right, so here we see evidence of how that slope difference actually plays out. So let's just focus on one standard deviation above the mean for age and one below the mean. And so here you can see that there's a more positive association between interview scores and job performance for people that are one standard deviation above the average age, okay? And for those people who are one standard deviation below, there's a less positive association here. So let's look at the simple slopes analysis here as part of the output. And you'll see here's one standard deviation above the mean for age, okay? And we see here that the estimated slope is 0.69, which is statistically significant. So that's that dark blue line there. We could also look at the mean too if we're interested in that. But let's skip down to most often we're interested in one standard deviation below the mean as well. And so here we see the slope value is 0.45, which is less than 0.69. And the associated p-value is statistically significant. So all of these slopes that we see here, and specifically that we're referencing one standard deviation above the mean and one standard deviation below the mean, are statistically significant and positive. It's just that for people that are older, and the relationship between interview scores and job performance is stronger and more positive. Okay? And so what this is saying is that the interview score differentially predicts by age with respect to performance. In other words, age moderates the association between interview scores and job performance such that those people that are older have a more positive association or stronger association between their interview score and job performance. Okay? All right, so that is evidence of slope differences there. All right, so the last thing that I'm going to do is let's do this one more time, and I just want to show you the special case with race here, just because the variable is a categorical variable, but it has more than 2 levels. You have Asian, black, and white here. So there's 3 levels to that categorical variable. I'm going to skip all the way back up here and just grab the same info, but for when we did gender. Okay, so let's copy all that we did there for gender, paste it below here, and just briefly come through. I'm going to delete the JTools information there, installing it, because we've already done that. And for the first step, we've already assessed the criterion-related validity of the centered interview variable with respect to performance evaluation scores. So we're good there. We found evidence of criterion-related validity, but now we need to replace the race variable, or the gender variable here, with race. Now, I do want to point out that we need to do something that is, at least in terms of the legal environment within the United States, typically, even if there's 3 categories of race, you in some ways dichotomize the race variable. So, a really coarse way of doing this would be whatever the majority group is. So if that's white employees, is one group, and the other level would be everybody else. I think a more specific way of doing this would be and a more refined way of doing this would be to compare different groups. Okay, so specific to groups. So we're specifically, this is totally arbitrary for this purpose, but let's just say we're going to compare Asian and white people in this tutorial here. Okay, so for the intercept differences, step 2, we're going to be using the reg.brief function again from the lessR package, and we're going to use the rows equals argument from that package, and we're actually going to specify a subset within that. So we're going to say when race is equal to, double equal to sign means equal in terms of the logical operators within R, Asian, okay? So that's one level, and then we're going to use that vertical line here, which is the logical OR symbol in the R environment, and we're going to say or race is equal to white. So what we're saying is select those people if their race is equal to Asian, or if their race is equal to white. So in other words, we're going to select those people where one of these is true. Okay. And so this is going to reduce our sample size here. Okay. And actually, I should point out that if we're really going to do this, we should also do this here for the criterion related validity step in step 1, because we want to know what is the criterion related validity when we have this reduced sample size where we're just looking at Asian and white employees. We've reduced our population scope here in other words. Here we have our output. We scroll down. Now you see this reduced sample size here. Okay, so we see in the analysis only 346 people were included here instead of the original 377 we saw in the other models, and that's because essentially what we did was we filtered out the people in our sample that identified in terms of race with Black or African American. And so here we can see that looking at our criterion related validity here for our interview selection tool with respect to the job performance outcome variable, that we see that the regression coefficient is positive and the associated p-value is less than 0.05. So we conclude that indeed the interview scores, when drilling down to just those individuals who are Asian and white as our population of interest, they still predict our outcome variable of performance evaluation scores. Okay. And in terms of variance explained, we see the R squared value, whether you're looking at the unadjusted or adjusted values, is around 16.16 or 16%. So the interview variable for this population explains about 16% of the variability in that outcome variable. And we do see that the associated p-value is less than 0.05 for model fit, which means that when we include for this population that interview variable as a predictor, it explains a statistically significant amount of variability, or it improves the fit of the model above and beyond a model that is a null model without any predictor variable. Okay, so now we're ready to come down to that intercept differences model here, where we're going to test for those and look for differential prediction in that regard. And so again, what we did originally here, these are just the names of the, we're just applying the rows equals filter here, or subset. And this is just what we did above. But now in this model, we have the additive model where we're adding the race variable here. Okay, so we're only going to be looking at race with respect to Asian and white here. So let's run that. Okay, so if we come to our output here, we see that, again, we're looking at 346 people here in terms of the sample of that we're working with when we're just looking at Asian and white people. And what we're interested in our estimated model section here is this estimate, this regression coefficient, which is negative 0.373 for race, and the associated p-value, which is less than 0.05. And so this is statistically significant, which means there's evidence of slope differences. And because race is appended with white here, it means that when comparing, when taking the outcome variable for white people minus that for Asian people, it's a negative value, which means that white people in this particular sample tend to have a lower intercept value. Okay? And the next thing that we can do is take a look at the R squared in terms of value, in terms of model fit. And we see that it's between about 18 to 19% there. And again, model fit, this model with 2 predictor variables fits significantly better than a null model with no predictor variables. All right, so we do have evidence of intercept differences here. Just as we did before with gender and with the age protected class variables, we need to specify a model, which we're calling the intercept differences model, or int model here. And we are using the lm function from baseR, which is the linear model function there, to do so. So again, it's going to be the same arguments as we had before, except now we need to use not the rows equals, but the subset equals, which is a specific, it's the same thing as above that we use rows, but specific to the lm function there. And let's just copy our conditional statement there so that we can specify that we just want to look at the data for Asian and white employees there. And let's also make sure that we switch gender with race there as well. Okay, so it should be your predictors are interview and race. Okay, so let's run that. Okay, and then now we're ready to probe the interaction because we did find that statistically significant, we found evidence of a statistically significant difference in terms of intercepts. So now let's come down here. All that we need to change from our probe underscore interaction function that we've been using before in the specific arguments is just change gender to race here. Let's highlight that. I'm going to open up the plot window here. Click run. Okay, and so this is just evidence of what we saw it before. So I showed you with that regression coefficient that was negative. It implied that the white people had a lower intercept difference than the Asian people here with respect to interview scores in relation to job performance, okay? So that's evidence of differential prediction with respect to intercept differences. A common regression line would not be appropriate there. Okay, so now let's finally go down and test if slope differences exist. We're going to replace gender with race here, gender with race here, and gender with race down here. And as before, we're going to add that additional argument that we were using with the reg.brief function, which is rows equals, and specify again that we're just looking at Asian and white employees, so subsetting down what we're looking at. And so let's go ahead and run this script here. And this time we're looking again at that interaction term, which is why we're using the asterisk between the 2 predictor variables. So let's click run. Let's look at our output here. Okay, so we're working with 346 people in our sample. What we're interested in our estimated model section is this last line here where we look at the interaction term, or in other words, the product term between race and the centered interview variable there. And we see the regression coefficient is 0.103. But what we're really interested in here is the p-value, which is actually 0.262. So this is a little off center here. But what this says is the interaction is not statistically significant. So in this case, we'd actually just stop here. Okay, we would stop here and say, okay, because we didn't conclude or didn't find evidence of slope differences here in this third step using our moderated multiple linear regression model, we wouldn't go forward and probe whether or not those differences exist or interpret them using a visualization like this. Okay, and if you were to find significant differences, then you would proceed forward with that and then examine those slope differences here. But stop here if you find that the interaction term is not statistically significant. Okay, so what did we learn here? Well, we learned that with race, there are intercept differences, but not slope differences. With age, there are both intercept and slope differences. And with gender, there are both intercept and slope differences. And so this is moderated multiple linear regression in the context of differential prediction, specifically for assessing the criterion-related validity and whether or not there's predictive bias with respect to different protected classes of a selection tool in relation to a criterion of interest, or in other words, an outcome variable of interest, which typically in a selection context would be some type of performance indicator or variable. So in this tutorial, you learned how to do a moderated multiple linear regression in R. Thank you.